Hello everyone, my name is Muhammet Kırık, and in this video I will be introducing a novel non-orthogonal multi-access method for the multi-user MIMO with the antenna number modulation. So let me start with what it is first. Multiple input, multiple output with antenna number modulation and adaptive antenna selection has recently been proposed as an effective transmission method that can make the selection of antennas to be both data and channel dependent simultaneously, which can result in having a much more improved performance in terms of reliability compared to index spatial modulation-based schemes. However, one of the main undesirable features of the MIMO-ANM-AAS, which is also the case in the spatial modulation, is the fact that not all the available antennas are utilized for the transmission, as some of these antennas are made inactive. To overcome this problem and utilize all the available antennas, MultiUser MIMO-ANM-AAS is proposed in this presentation as a novel non-orthogonal multi-access data transmission method that targets serving multiple users by dedicating the antennas used for implementing A&M to serve far user, whereas the remaining antennas are used to send data for a near user. The fundamental idea behind the proposed scheme is to serve a far user who is located in a distant location from the transmitter by antennas that are defined and utilized by the A&M modulation, while the remaining antennas are deployed to transmit a lower powered data stream that is intended to be sent to a near user who is located in a close proximity from the transmitter. By implementing this method, the near user can simply be served by allocating low transmission power to the antennas that are not used by A&M, whereas the far user is served by the antennas involved in the A&M modulation. By using such a transmission scheme, two users can be served simultaneously by a single MIMO-ANM architecture, and the obtained system reliability of the transmitted data stream for far user can be enhanced, while the capabilities of the antennas not used by the A&M are not wasted but instead utilized to serve an additional user, thus resulting in improving the overall spectral efficiency of the system. So let me go over the system model of the proposed scheme. So imagine that we have a incoming bits group that we want to transmit for the far user, and we have another incoming bits group that we want to transmit for the near user. So to start with the far users data bits, we are basically separating those bits into two different groups as main bits and A&M bits. So in the A&M bits part, we are sorting the channels by the capacity or their channel capacities by exploiting a A&M bits mapper, which I will be talk about it in the following slide. And we decide which antennas are offering high quality and which antennas are offering low quality. And after that, we take our main bits and we modulate them by the BPSK, which by the way can differ. We can also use QPSK and etc. But in this case, we choose to use BPSK modulation. So after the BPSK modulation of the main bits, we send them through the high quality antennas, and we do the power allocation for the far receiver. On the other hand, the transmitted bits of the near receiver is also modulated by the BPSK, but for the transmission of this user, we use the low quality antennas that we did not activate for the transmission of the far user's data, and we also do the power allocation at this point for the near user, and we transmit our data. So this is the A&M mapper that I just talked about. So in this case, if our A&M bits are 0, 0, we are activating one antenna, but we never say which antenna we are activating. It might be the first one, second one, third one, or fourth one. So this is the point that the antenna number modulation scheme differs from the index modulation and spatial modulation. The A&M antenna number modulation is both channel and data dependent. So if it is 0, 1, we are activating two antennas, but we never say which two. So in this case, we have 6 different possibilities to activate two antennas out of 4 antennas. And for 1, 0, we are activating 3 antennas. We have 4 different scenarios here, and for 1, 1, we are activating all the 4 antennas. So at this point, the transmitted data for the far user and near user will also differ. So for the transmitted data of the far user, the first formula is given. At this point, as you can see, we use high power to transmit the far user's data because the user is far away from the transmitter and it needs more power to get the signal from the transmitter. So at the transmitter, we are transmitting both the far user's data and near user's data at the same time, and our total transmitted signal is Y. So this part of the Y is our far user's data, and this part here with the P low, it is our near user's data, and at the end, of course, we have our white noise. So to acquire the near user's data, we basically need to subtract the far user's data from the whole data, so eventually we can come up with the near user's data. So if we mathematically do that, we are coming up with this formula, and after all, this is the YN, which is the transmitted signal for the near user. So to illustrate the process, we can take a look at an example now. So imagine that we have the incoming data stream for the far receiver here, and we have the incoming data stream for the near receiver. So we want to transmit this data. So at the first bit, which is 1, we can see that the A&M bits are 1, 0, which we can infer that the 1 will be transmitted through 3 antennas because of the rules that was defined by the A&M mapper. So in the figure 3a, you can see that we are transmitting 3 antennas. We are using 3 antennas to transmit the data to the far user, but on the other hand, we have another one here for the near user, and since we are using 3 antennas for the far receiver, we have only 1 antenna in the system, which will be deployed to transmit the near user's data, which we are using it here. Similarly, we have a 0 here, so we want to transmit this 0, but we also want to transmit this 1 here for the near user. So if we check out the second symbol of the A&M bits group, we see that we have a 0, 1. So 0, 1 means 2 antennas, so it means that this 0 will be transmitted through 2 antennas, but we also transmit this 1 from the remaining 2 antennas. So what do we mean by that? You can see it in the figure 3b. So these green ones are deployed to transmit the far user's data, while the red ones are used to transmit the near user's data. And similarly, this 0 will be transmitted for the far user, and another 0 will be transmitted for the near user. So if we check out the third symbol of the A&M bits group, we see that we have a 0, 0, which means transmission activation of only 1 antenna for the far user. So in that case, while we deploy only one antenna for the transmission of the far user, remaining 3 antennas will be deployed to transmit the near user's data. And at last we have 1 here and A&M bit symbol. The fourth A&M bit symbol is 1-1, which means the activation of 4 antennas. So in that case, all the 4 antennas will be deployed to transmit the far user's data, and unfortunately we won't have any antenna to transmit the near user's data here, so she won't be served during the transmission. So at the receiver, we have 2 different receivers for the far user and the near user. So for the far user, we have the MIMO receiver. We have 2 different groups, the main bits group and A&M bits group. So we are demodulating them separately, and eventually we are coming up with our received data for the far user. For the near user, though, we have a different situation, because the near user can get all the data that was transmitted for her and also for the far user. So at this point, what we need to do is as follows. So we have the MIMO receiver, and we do the equalization here, and we will decode the far user's data by the BPSK demodulation, and we will come up with the far user's data. But this is not what we want, so we do another equalization at this point, and we do a successive interference cancellation. We will basically subtract the far user's data from the whole data to come up with the near user's data, and demodulate the near user's data, and at the end we are going to come up with the received data for the near user. So these are the simulation results that we have coded in the MATLAB. In the figure 8, we have the beta error rate of the far user for the A&M bits stated in the green line, main bits stated in the pink line, and their average as the transmitted data of the far user, which was stated in the blue line. In figure 9, we are comparing the data of the far user and the main user, near user. So the red line represents the beta rate of the near user, and blue line represents the beta rate of the far user. As you can see here, the beta rate of the far user surpasses the beta rate of the near user, which was what we're actually trying to do. And in the figure 10, you can see the simulation results versus the theoretical calculation results. As you can see, the dashes and the straight lines are on top of each other. The dashed lines are representing the simulated results, and the straight lines are representing the theoretical calculations. So they are on top of each other, which means our calculations and simulations are legit, and they can actually implyable on the future wireless system. So this was it for my presentation. Thank you for your time.